Welcome to www.admart.com training video for a program titled Engineering Software. This program has an extensive number of algorithms interfacing various sheets. The program was created in 1995 and uploaded online in the beginning for the utilization of the Internet. The program allows the user to input their present process relative to grinding and hard turning and have a software program configure the process for the application input. It is both a mirror of your present process as well as a product that will give you data for input for how the software has calculated what is computed to maximize your process. Some people refer to this program as the predictor. It was written in an old product of Sun Microsoft Java. I chose to use Java in the early 90s because it was safe from hacking. The product is on my server and Java applets are downloaded on your computer to allow you to interface with the program. When you close the program, you must start over with the next download. It also allowed me the option of making changes without sending out disks, but uploading to my website long before it was the norm. This product can be purchased for non-recurring subscription of weekly or monthly and an annual recurring subscription on a yearly basis. You are given an ID and password and you can download anytime 24/7. First-time users must download the applets and then your computer is off and running. Any new computer will need this first-time setup. My recommendations is to print as a PDF file and save relative to applications. This way you can not only use it for other close applications, but you keep a running history of the progress you have made on each application over time. Because of the size of this program and the number of different sheets, I'm going to break up the presentation into 3 different videos. This is training video number 3. Reviews for hard turning, insert testing and machining cost models. There is a grinding cost model program, but it is similar to the machining cost model. And I will skip the surface grinding program for another presentation at a later date. Let's begin with the hard turning, which is up on the screen as we see it. All of the maroon colored font cells, which as you can see, like largest diameter, average smallest diameter, must be filled in order to continue. We have average of face diameters, average diameter and lengths of the diameters if you're turning, grooving and parting. So we have really faces, diameter turning, grooving and parting as options for this process. So we've picked the largest diameter for the face grinding as 1, and we're having 3, in other words, 3 inches in diameter. The smallest is 2, and the number of like faces is 1, which is what I was referring to. And the average total depth of stock on the face is 5 thousandths. In the blue, greenish blue colored sidebars are where the calculations are coming from off the software. The inputs that you input are what will show up as the model calculations below. So on the grooving part, this demonstration is taking everything into account. It has absolutely nothing to do with anything that would be real, but rather just to give you an idea of all the data that can be input and how the results work. We're doing a grooving part, and we have a full width of plunge, no. Therefore, it's calculated how much we would need. So the average total width of the groove is 125, so we'd be taking a plunge over 0.625. The average depth of the stock per side is 20 thousandths. On diameters, I'm starting with a 2.375 average starting diameter, average turning length width of 2.878, number of like diameters 1, average total depth 15 thousandths. The interruptions, we can have a choice of yes or no, and I'm putting in yes, because a lot of people don't realize that interruptions is not an issue depending upon the application. This application will be no problem whatsoever. And then we go to the left again. I want to show you we have materials, and the materials range all over from tool steel down to non-metallics and ceramics and carbide. And we picked carbon steel. We'll come back to that. Part hardness, we've chosen 55 to 59. Surface finish, we've chosen 16 to 22. And then we put in the style we chose CNMA, 432, 20 by 4. The edge length of the usable PCD, we could have the typical 40 thousandths, which would be on a mini tip, because with fabricators, you're not stuck with what a manufacturer can make with his own insert material, but rather you can have anything you want. Let's say you want to take 100 thousandths depth of cut. Not a problem if you have enough land to work with, and the fabricator can do that. So we've chosen 125 in this case. Coolant, no, we're going to go dry. We could have had yes, and we could have put in the coolant type here, and you'd had a choice of water, oil, water soluble, or synthetic. We're going back to no. Based on this material, carbon steel, its typical edge prep they're showing is 4 by 20 up to 8 by 30, whatever degrees. It's also saying that the material we should be using is a low PCBN content. It's giving you a generality to go to your manufacturer to know and let them know what you're going to need if you're trying to make those decisions on your own in some environment for testing with some little secrecy to it. Over to the right, we've got roundness, cylindricity, perpendicularity, concentricity, tool runout, and here are the tolerances. Now, I did this on purpose. You can see that we have 4/10 roundness, 5/10, 5 times 5/10, and we've kicked it off because I put in a default relative to what I feel. This is my opinion. I feel relative to the machine tolerance and the machine can do versus grinding. So in turning, I look at it as being a 5/10 if you have any kind of CPK value whatsoever, is the break-off point. So you see you have a warning here. Warning, tolerance input indicates that hard turning may not be suitable. If I were to change that to 0.0005, then it would go away. So that kind of input is important for us to at least get some idea as to where you are relative to give you an idea that maybe this is possible or maybe not possible. Could it be lower? I'm sure. But if we didn't have these ridiculous things called CPKs that we have to hold, then yes, I would be feeling much more comfortable to say 3 or 4/10. Now, let's look what happens. Right now on the carbon steel, it's recommending 3 to 800 surface foot all the way down the line. We input 400, which means it's converted to, depending upon the application, the work RPM max on the OD turning is 652. Work RPM max using the numbers that we input for the grooving and parting, 798, or 6 rather, and the face is 764. If we to change the diameters, they would change. But also, let's say we decide to go on the first one, we're going to go at 800. You'll see the RPM change to 1,304. So it's automatically converting for you based on the surface footage, what you need, and then of course you depend on what you actually have capable of on your particular machines that you're working. Well, let's decide that we're going to go with, let's go down to 300 series stainless. It's not applicable. It's not a place that can be used for hard turning. Not considered good application. Let's assume that we go to gray iron. Wow, big difference. Now we go to high PCBN content, solid PCBN. But we have a lot higher potential than we had with the hard steel. Let's go to something like carbide fired cobalt, PCD, 50 to 100. Everything changes. Now if we were to go carbide greater than 16, we go to high PCBN, solid PCBN, and we have a whole different range of speeds and feeds. So as you change the material, you're going to see a change relative to what we suggest to be run. Once everything is filled in, then at the bottom, this is the input that you input, not what's over here suggested, but relative to your input, 400, 15 thousandths, da, 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 da. Then the time in the cut, all of the numbers are shown so that you get an actual cycle time. So for this process, we have 33.32 seconds for the diameters, 5.89 seconds for the faces. Faces diameters 39.21, grooving and parting 0.38 seconds, 39.59. Then you input, and by the way, it gives you your metal removal rate, cubic inches per minute of each application. And then you can input your cost per edge. over on the outside. So OD insert cost per edge is $39.50. You enter these numbers in yourself. The grooving tool I input $75. So the computer is now calculating that based on the amount of material, the depth you're trying to go, the surface footage that you're working, the material you're trying to machine. This is what it is calculating would be your number of pieces per corner. The OD application 63, the face application over 1,000, OD face 59, and so forth. You can enter in what you actually think you're going to get, or you actually shown. Let's say you only got 50 on this process. You didn't get the 63. There could be rigidity issues. There could be a lot of things, even down to the manufacturer, the transition of the edge prep doesn't match what you're seeing. So now we show that 79 cents a part versus before, let's say we had 56 cents. So it actually calculates your insert cost per part based on your input cost and the number of corners you actually got. So cost based on actual tool life per corner. The next sheet that we have available is a sheet that allows the user to test one product against another. One PCBN insert against another, carbide against PCBN, one carbide company versus the other, whatever you want to do. So this is going up to 4 diameters, 4 faces, and you input the depth of cut for each. As you can see, we've entered 10, 15, 10, 15. We enter the finished diameters, which calculates again to the RPMs you're looking at, the cubic inch material to stock that you would be achieving based on what you've already input for each one. I filled everything out, which obviously would never happen, but just to show you how all these numbers correlate. Again, the average RPM, all the material stock removal. And now we get the bottom line. Time in the cut, 267.1 seconds. Time in cut of faces, 22.9. Total time in cut per part, 289. All the way down, each one. And then it gives you the linear inch per tool and the insert cost per corner, because we've already put in the number of corners, number of parts per corner. Everything has been entered that would be needed to do this calculation. So this is just an extra little sheet that allows you a lot of flexibility if you want to compare one test tool against another test tool. And I've done such similar to the machining cost model. I have a machining cost model and a grinding cost model. These are absolutely identical for all intent and purposes, except for some things like in the grinding you would have potential for rolls where you wouldn't be seeing that machining cost model, but all the rest is the same. So you'd enter your normal information relative to your company and this tool description. But now you need to have parts produced per shift, parts produced per year. These are critical. You see they're also, like in before, in the maroon colored cells. You have tool cost, or insert cost, where you get the cost of the new tool, number of inserts per tool, number of corners per insert, cost of regrinds, number of regrinds per tool, total parts per corner. Then your cost per corner, your tool cost per part. All this goes down. You have production hours, tool setup, labor rates, and labor rates can change. I entered this so that you have maybe one labor rate for maintenance, one labor rate for tool changing, one labor rate for production. You can enter all these in. Scrap cost, value added cost per part, rework cost, inspection cost, inventory cost, even down to the percent rate of capital that you'd have to consider. And at the bottom, all your costs, tool cost per part, online labor cost, everything would be broken down relative to the particular part that we're evaluating. And your total machining cost per part would then be, in this case, 56 cents. Quickly over to grinding, just wanted to show you the same thing. And again, what the actual cost per part would be. I hope this is helpful to you, especially for those that are looking at hard turning and whether or not they should be using hard turning versus grinding, or just to evaluate and have some idea of what the starting parameters should be and how those parameters are relative to what they're trying to do. Please visit our website at www.admart.com and take the time to listen to our audio description of what our site has to offer and review each page. Our Pay Products page has a number of products for purchase, and each is in a zip file. And when purchased and opened, please remember always to extract all after downloading the zip file. Has an audio for training. Also, each product has a link to a video like this one on YouTube as an additional training tool. If you have any questions or suggestions, please contact me, Dale Savington, at the website at admart.com, and then from the Contact Us portion located on each page. Thank you.